so this will be our first video over Chapter 20. Chapter 20 is the beginning of our discussion of electricity. We're going to be talking about electricity in Chapters 20, 21, and 22, and then we'll be finished. You guys probably all studied electricity and positive and negative charges and things back in middle school, 9th grade. So you may kind of think back on that a little bit. All materials are divided into two categories. We have conductors and these are materials that allow charge to flow easily. Conductors transfer charge. If you have a conductor, and the most common conducting materials are just everyday metals, copper, aluminum, silver. If it's metallic, it probably is a conductor. If you put some charge here, you transfer a bunch of excess charge here, it won't stay there because it allows charge to flow. One of the things you probably learned in middle school is that like charges repel one another. So very quickly what you would see instead is that any excess charge will distribute evenly. Now, conductors include, of course, metals, but a couple that you might not think of would be moisture. In particular, humid air will conduct electricity, whereas dry air probably wouldn't. And human bodies. Now, that has some implications. If I tried to charge a metal rod in my hand and I got a piece of silk, one way you can, and you rub and you rub and rub on that metal rod, what you're going to find out is probably not much charge will ever build up on it. And the reason being is, let's say this marker is my metal rod. Any excess charge I put on this will quickly distribute over my whole body. So it's going to be really, really hard to charge something by holding it in your hand. Now, if you had on rubber gloves where you were insulated from it, then it might work. But you will probably conduct electricity. One of the reasons we don't have a lot of static electricity in the wintertime is because the air is very dry, and so charge doesn't build. I'm sorry, I said that wrong. The reason we don't have static electricity in the summertime or spring around here usually, most of the time that air is really pretty humid. But in the winter when we run our heaters, the air inside our homes and our offices gets really dry. And it's really easy when the air is dry to have a static charge build up. If you walk, it might build up on your carpet as you shuffle across the carpet. And then you go and you reach for a doorknob. Well, the doorknob conducts electricity. So very quickly when you touch that doorknob, you'll get a shock as it conducts that excess electric charge off of you. Okay, so those are conductors. Okay, anything that does not conduct electricity falls into the other category. And that other category is called insulators. Insulators are materials that do not allow charge to flow. they don't transfer charge. What that means is if I have an insulating rod and I put some excess charge on it down here, that excess charge is going to stay exactly where I put it. Now, I didn't mention, but what's really the big difference here? The difference is when you have insulators, they have tightly held outer electrons. When I say they, let me rephrase that. The atoms that make up an insulator have tightly held outer electrons. I don't know if you've taken a chemistry class, but in chemistry, these outer electrons are called valence electrons. Okay. Generally speaking, atoms are very happy when their outer shell is full. So when you have insulators, you have materials where that outer layer of that atom is full or almost full, and they hold on to their electrons really, really tightly. Now, when you have a conductor, the atoms of a conductor have very loosely held sometimes they're called free outer electrons. Again, if you had chemistry, we call those valence electrons. Most metals will only have 1 or 2 electrons in that outer shell. And since atoms like to have a full outer shell, the easiest thing to do is just get those 1 or 2 electrons away. So those metal conductors have what we call very loosely held or free electrons in their outer shell. They're very happy to let those flow and get rid of them. Okay. So we know when the weather's dry, static electricity can build up on things. I don't know if you've ever, in a winter day, been shocked when you went to open your car door because the outside of the car had built up this static electricity. That can be a problem for some things. You don't want to build up a static. To prevent static charge, from building up, some objects are grounded. Go back to this word static. I've been saying it, we're all familiar with the term static electricity, but basically all electricity falls into 2 categories. We talk about static, that comes from the root word for stationary. That refers to electric charges that are essentially just sitting on things at rest. That's different than the electricity we'll cover in chapter 22, maybe it's chapter 21, which is electric current. That's the flow of electric charge that we use to turn on the lights or anything. We know what electricity is, current electricity. But now we're really just talking about charges that are more or less at rest. Okay, so we know static charge can build up on things. It can be problematic. If you drive a great big tanker truck, you don't want a whole bunch of static charge building up on the outside if you've got a tank full of flammable or explosive materials inside. So we ground these things. And when you're grounding, the object is literally connected to the ground. The object is connected to the earth by a wire. It's possible some things can be connected to something else that's also very large, but the earth is a massive conductor. It can gain millions and millions of electrons, or it can donate millions and millions of electrons, and still for practical purposes remain neutral. It's just too big to build up a charge. So if you've ever driven behind like an 18-wheeler and from behind it looks like something's dragging, you literally can see this wire hanging down that's dragging along the road, and it almost looks like maybe something came loose. Well, that wire is there deliberately. It discharges by connecting the truck to the ground. No excess charge will build up on the outside of that truck because it's grounded. It's connected to the earth, and that charge can flow freely down that wire to the earth. Now, on a much smaller scale, you may or may not have ever noticed that shopping carts are sometimes grounded. I haven't looked lately, but Walmart, if you look, there used to be a little wire that was hanging down underneath your shopping cart, and its purpose was the exact same. It was so the shopping cart, those metal shopping carts, would not build up a static charge, and then you go to touch one, and you get shocked. So, literally what happens is if you have something, here's the earth. Remember, the earth can gain or lose lots and lots of electrons, and something up here has accumulated a bunch of extra electrons. All I have to do is connect it to the earth with a wire, or wires will conduct charge, and very quickly those charges will flow down into the earth. This will end up neutral. And believe it or not, for practical purposes, the earth will still be neutral. I don't care if it gains 200 million electrons. It's so large, it's probably still neutral. Okay, we've been talking and using some vocabulary, but we want to kind of go back over a few things that I feel like you should know, but I want to be sure you know. First of all, there are two kinds of charge. Because there are two kinds of charge, electric forces are different than gravitational forces. Gravitational forces are always attractive. Every mass in the universe is attracted to every other mass in the universe. But there's not two types of mass. There are two types of charge, and one of the results of that is that electric forces can be attractive or repulsive. In fact, we know that opposite charges attract and like charges repel. Okay. Now, it was Benjamin Franklin an American scientist and statesman who was the first person who called the two types of charge positive and negative charge. He made a really excellent choice in naming them positive and negative because we can use positive and negative numbers to describe them so well. But honestly, he could have just as easily decided to call them any kind of opposite. Up charges and down charges, or black charges and white charges, or anything at all. When it got time to name quarks, which we're not studying quarks right now, but they did get unusual names like up quarks and down quarks and top quarks and bottom quarks. But we're really lucky that Benjamin Franklin decided to call these two types of charge a positive and a negative charge. If I take two objects, and it depends on which two objects, but certain combinations, if I rub them together, I can transfer electrons. Now, one of the things you should probably understand is it's almost always going to be electrons that transfer, and there's really good reason. When we understand the atom better, we'll realize that positive charges, which are protons, are always trapped inside the nucleus of atoms. Positive charges are really hard to do anything with because they are literally in the nucleus held together by the strong nuclear force. But it's all those electrons that are outside that nucleus that are often free to move, and that objects will donate a few electrons or accept a few electrons. Okay? So, when two objects are rubbed together, electrons can be transferred from one object to another. The result of that is one of those two objects is now going to have a positive charge, and one of those two objects is now going to have a negative charge. So, for example, if I have a piece of rabbit fur, and I have a PVC pipe, a little piece of PVC rod, something like that. And they're initially both neutral. Neither of them has any excess charge. But if I start charging, if I take this rabbit fur and I start rubbing it on this PVC rod, what's going to happen is that rod will give some of its electrons, will be transferred off the rabbit fur onto this piece of PVC, and the result will be is my rabbit fur is now positively charged. It used to have an equal number of positive and negative charges. Anytime something's neutral, it's got an equal number of charges. Millions and millions and millions of charges. Usually when we talk about charge, we're talking about an excess of some sort. So, this rabbit fur is positively charged now. My PVC pipe is negatively charged now. Okay. However, what's really important to understand is these two charges have to be equal and opposite. If these were neutral to begin with, that means in all we had equal numbers of positive and negative charges. So if this gained a charge of plus Q, then this rod has to have a charge of minus Q. Okay. This is because of the principle of conservation of charge. We can never create charge, we can never destroy charge, but we can transfer. So if I transferred 10 microcoulombs of charge, negative charge, off this onto this, this could have a charge of positive 10 microcoulombs. This could have a charge of negative 10 microcoulombs. Okay? That's a really, really important principle called conservation of charge. Conservation of charge. Really, really important idea. So put a big star by that in your brain. Says charge cannot be created or destroyed. It can only be transferred from one object to another. It's a really important idea. It's saying that all of the charge that exists in nature exist in nature. We're not making more charges. We're not making more protons and electrons. We're also not destroying any charges. However, most matter is naturally neutral. Okay? But if I rub, like you ever done a load of laundry and you throw a bunch of nylon underwear in with a bunch of cotton socks and they all tumble around together, even though they were all neutral when you put them in the dryer, all that tumbling around, the friction causes some of the electrons to transfer off of, I think they transfer off of your socks onto the nylon panties, and now you've got positively charged socks and negatively charged panties, and they want to stick together. When you pull them apart, you hear that snap, crackle, pop of static electricity. We didn't create charge when we threw our laundry into the dryer, but some of the charge transferred, leaving us with some negatively charged items and some positively charged items. Okay. We have studied, I want to say, 3 of the 4 major conservation laws, or basic conservation laws in physics. There are 4 basic conservation laws. This sounds like a wonderful question for either test 3 or for the final. They are conservation of energy, conservation of momentum, conservation of electric charge, and conservation of mass. We don't create or destroy mass. We cannot create or destroy energy or momentum or charge. Okay. Sometimes we put a little restriction on a particular, like a momentum we may talk about in a closed, isolated system. But the reality is, if we treat the whole universe as a closed, isolated system, we see that all 4 of those things are always conserved. We cannot create them. We cannot destroy them. I'm going to talk just a little bit more about matter. We've talked about atoms a little bit. And you guys are going to be doing some projects about atoms, in particular the different models of the atom. But basically we know that atoms are all made up of 3 things. And those 3 things are protons, those are positive, and they are in the nucleus. There are also neutrons. Neutrons are particles, they're about the same size as a proton. Protons and neutrons are really heavy compared to electrons. They're about 1,800 times heavier than an electron. And they are neutral, so they don't have any charge. And they are also found in the nucleus of atoms. And then finally we have electrons. They're negative, and we find them surrounding the nucleus. in what is now known as the electron cloud. You may still see pictures of atoms that show the electrons that look like they're orbiting, like planets orbiting the sun, but we know it's not really orbits. It's so much as it is there's just this cloud of electrons in certain locations which we think of as orbits, or maybe the more probable locations. Atoms are all neutral. Atoms have an equal number. So if I have an atom and here's my nucleus and it has a charge of +3 in it, that means it has 3 protons. Maybe it's got some neutrons because neutrons won't affect that charge. We've got the nucleus. And then surrounding that, we would have 3 electrons orbiting around in the cloud, okay? They'll be moving around. But atoms generally are neutral. They have an equal number of protons and an equal number of electrons. Now, sometimes atoms donate an electron. If they give away an electron, this is going to have a +1 charge because now it's got a +3 and only 2 electrons. That's called an ion. That would be a positively charged ion. Sometimes a proton or an atom will accept an extra electron, in which case we get a negatively charged ion, okay? But I'm really not wanting to talk about the chemistry. I just want you to understand that generally speaking, all of the atoms that make up this sheet of paper, the number of positive charges and the number of negative charges are equal. This paper is neutral. Almost all matter is naturally neutral. So when we talk about something having a charge of 3 nanocoulombs, let's say it's +3 nanocoulombs, that just means it has more protons than electrons, and that difference is 3 nanocoulombs. Okay? If it's got a charge of -2 microcoulombs, if it's negative, it means it contains more negative charges, more electrons than protons. And the charge of those extra electrons is, I forget what I said, -2 microcoulombs or whatever I said a minute ago, okay? So generally when we talk about something being charged, we mean it has excess protons or excess electrons, because we know most of the time matter is neutral. If it's got some extra electrons, it's going to have a negative charge. If it's got more protons, it's got extra protons, it's missing some electrons, it's going to have a positive charge. Okay, I think I'm going to stop here for this one. I'll be putting more notes about chapter 20 online soon.